Right now, 10.4 billion light-years from where you are sitting, there is an object so massive that its shadow alone is wider than the orbit of every planet around our Sun. It does not move, it does not cool, it does nothing that the cosmos does not allow. It only sits there, in a corner of the constellation we have named Canes Venatici, the hunting dogs. A point of light, faint blue-white, no larger to our telescopes than the head of a pin held at arm's length. The catalogue number is 618. The catalogue name is Tonantzintla 618. The community calls it, with the brevity that astronomers prefer, Ton 618. That faint point of light is the visible record of the largest single black hole that human beings have ever measured. Tonight we are going to walk through what that means. You do not need to hold every number. Some you will. That is enough. The light we are about to discuss left its source when the universe was roughly a quarter of its present age. By the time the light arrived at our telescopes, the Earth had cooled, the oceans had filled, the first single cells had appeared, the dinosaurs had risen and gone extinct, mammals had crossed continents on land bridges that no longer exist, and a species had begun, in the last small fraction of that span, to point glass at the sky and ask questions about what it saw. We have a couple of hours. There is no urgency. If you have come here to rest, let this carry you. There is no urgency in what we are about to hold. It is older than memory and farther than any place you will ever go. Now let us pull back. Let us look at where this small point of light sits in the order of things, and what kind of instrument was watching when it was first noticed. The story begins not at a great observatory, but at a modest one. In the spring of 1957, on the slopes of an extinct volcano outside the city of Puebla, in central Mexico, a photographic plate was being exposed. The observatory was called Tonantzintla, after the village beside which it stood. The name comes from the Nahuatl, meaning the place of our little mother. It is an older name than the observatory by several centuries. The plate was part of a survey. The job of the survey was to photograph faint blue stars, hot, blue, dim points that did not show up easily on visual catalogues. The expectation was that the survey would record subdwarfs and hot white dwarfs, the faded ends of stellar life cycles. 2 astronomers oversaw the work that night. One was named Iturbide, the other was named Erro. They were cataloguing the southern sky's faint blue population, one entry at a time. The plate from that particular evening, when it was developed and examined under the lamp in the observatory's small darkroom, contained the usual selection: white dwarfs, subdwarfs, a few unfamiliar streaks, and one object, somewhere in the field of Canes Venatici, that looked nothing more than ordinary. A faint blue point, magnitude 15.9. It was entered as the 618th object in the running catalogue. Ton 618, Tonantzintla 618. A clerical entry, a number on a card. It would sit there for 8 years. Nobody noticed it. The plate went into the archive. The catalogue was published. Astronomers consulted the list for what they needed and moved on. The Tonantzintla survey produced thousands of entries. Number 618 was one among them. Faint, anonymous, unremarkable. The point I want you to hold here is the one nobody could have known at the time. The faint blue speck on that plate was the brightest single-point source of energy that has ever been recorded by an instrument made on Earth. The point was already pouring out. In the moment its light was captured by the photographic emulsion, more energy than the combined output of 40,000 galaxies like our own. The energy had taken 10.4 billion years to arrive. It had been travelling toward that plate, in a particular small dome in central Mexico, since the universe was 3.3 billion years old. It had passed through clusters and voids and the haze of intergalactic dust. It had been redshifted by the expansion of space itself. It had arrived. It had registered. It had been catalogued. Nobody noticed. This is one of the textures of the work when the work is the night sky. We do not always recognise what we have found at the moment we find it. The thing recorded on the plate had passed through the gaze of 2 astronomers and an exposure lamp, and the system had done its job. The discovery, when it would come, would be a slow one. Decades long. Now let us pull back, fellow night watcher. The story of Ton 618 is going to take us, in a slow, careful arc, from a small dark room in Puebla to a region of the universe so distant that the light we see from it left before our solar system had finished assembling itself. There is, I want to be clear, nothing dangerous in any of this. TON 618 is so far away that no signal from it could reach us in any humanly meaningful time frame. Its gravity is felt, in any practical sense, by nothing at this distance. We are not threatened, we are not addressed, we are not the subject of its attention, we are only its witness. And yet, what it is, when we sit with the measurement, is a thing the universe is not supposed to contain. Let me bring that closer. The number we are about to discuss, the mass of the object, is what makes the rest of the story matter. Without that number, TON 618 would be one faint blue speck among many. With the number, it becomes a problem. The mass is 66 billion solar masses. I want to take that apart slowly. A solar mass is the mass of our Sun, roughly 2 times 10 to the 30th kilograms. 1,000 Earths would not equal one Sun. 100 Jupiters would not. The Sun is a star of unremarkable size. There are stars larger, there are stars smaller. Our Sun sits roughly in the middle of the distribution, 66 billion of those. If you took the mass of the Sun and multiplied it by 66 billion, you would have the mass of TON 618. There is no easy way to picture this number. The mind does not hold 66 billion of anything. The mind holds 1, the mind holds 2. The mind holds 10 or 12. After that, what we hold is the word for a number, not the number itself. So let me try another translation. The center of our own galaxy contains a black hole. We have known this since the early 1970s. The black hole at the heart of the Milky Way is called Sagittarius A star. Its mass is 4.3 million solar masses. By the standards of black holes anywhere, 4.3 million is a respectable size. The supermassive class begins at roughly 100,000 solar masses. Sagittarius A star is 50 times the lower bound of supermassive. TON 618 is 15,000 times larger than Sagittarius A star. The black hole at the center of M87, the galaxy whose central object was the first ever photographed by the Event Horizon Telescope collaboration in 2019, is 6.5 billion solar masses. That image, the orange ring with the dark center, the photograph that traveled around the world, that is what 6.5 billion solar masses looks like, when the conditions of imaging are perfect and the instrument is the size of a planet. TON 618 is roughly 10 times more massive than that. There is no image of TON 618. We do not have the resolution. The Event Horizon Telescope was built to image M87 and Sagittarius A star. It is not pointed at the quasar in Canes Venatici. The mass is known not by photograph but by measurement of the light that pours out of the disk surrounding the hole. That disk pours out more light than 4,000 Milky Way galaxies combined. I want to ask you to hold that for a moment. A single object, in a single small corner of a constellation, radiating the equivalent light of 4,000 galaxies. That is the engine. The disk of TON 618 is what we see. The hole itself is invisible, as all black holes are. What surrounds it, the orbiting maelstrom of plasma falling toward the horizon, is what produces the light. The plasma is heated by friction, by tidal forces, by the gravitational compression of the inflow. The disk near the inner edge reaches temperatures of around 100,000 degrees Kelvin. That is roughly 17 times hotter than the surface of the Sun. The disk is enormous. The luminosity is appalling. We can pick it out faintly across 10 billion light-years of empty space because the engine never stops. That is the brightness of TON 618. The brightness is the consequence. The mass is the cause. Now let us hold the cause for a moment. 66 billion solar masses. That mass, compressed into the geometry of a black hole, defines an event horizon. The event horizon is the boundary beyond which nothing returns. Once light or matter crosses that boundary, the geometry of space-time no longer allows return. The radius of the event horizon is set by the mass. The relationship is simple. The radius in kilometers is roughly 3 times the mass in solar masses. In kilometers. For TON 618, that calculation gives roughly 200 billion kilometers. 200 billion kilometers. I want you to hold that against something familiar. The orbit of Pluto, the most distant of the major bodies in our solar system, has a radius of roughly 6 billion kilometers from the Sun. The event horizon of TON 618 is more than 30 times that. The Voyager 1 spacecraft launched in 1977, after 47 years of continuous flight, has reached a distance of approximately 25 billion kilometers from Earth. It is the most distant human-made object. It crossed the boundary of the heliosphere in 2012. Its signal, when it sends one, takes more than 20 hours to reach our antennas. The event horizon of TON 618 is 8 times farther out than Voyager has travelled. If you were to place TON 618 at the centre of our solar system, in the location of the Sun, the event horizon alone would swallow the orbits of every planet: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, the Kuiper Belt, the scattered disk, the inner Oort cloud, all of it, inside the horizon. The horizon would extend beyond Voyager 1's current position. The horizon would extend beyond the heliopause. The horizon would extend into the dark, well past anywhere any of our spacecraft has ever travelled. And at the boundary of that horizon, the geometry of space-time would have folded over itself such that no light, no signal, no influence of any kind could ever escape from inside. That is what 66 billion solar masses looks like in geometry. This is the first thing about TON 618 that is not supposed to be possible. Now, let us pull back and let us walk slowly through how we know any of this at all. Because the leap from a faint blue speck on a photographic plate in 1957 to a black hole of 66 billion solar masses is not a small leap. It is a 47-year arc of measurement, refinement, and remeasurement, conducted by a slowly converging community of researchers at observatories scattered across 3 continents. I want to walk you through that arc because it is one of the quiet stories of how we come to know the universe. In 1965, Allan Sandage, working at Mount Wilson, looked again at the Tonantzintla catalogue. By that year, the category of quasi-stellar object had been formally established. Martin Schmidt at Caltech had identified the first one, 3C273, 2 years earlier. The category was new and strange. It described point sources of light, indistinguishable from stars on photographic plates, that nevertheless showed enormous redshifts. The redshifts implied vast distances. The vast distances, combined with the intensity of the light, implied luminosities that were difficult to credit. Sandage looked through the Tonantzintla list. He flagged objects that had the spectral character of quasi-stellar sources. Number 618 was one of his flags. The blue colour, the faintness, the apparent stellar nature combined with the spectral signature of broad emission lines was consistent. He noted it. Later that decade, optical spectroscopy was performed. The spectrum showed redshifted lines of hydrogen and magnesium, identifiable from laboratory measurements. The redshift came back at z equals 2.219, a large number. It places the object, in cosmological terms, at a co-moving distance of approximately 18.2 billion light-years. In light travel terms, the distance is 10.4 billion light-years. These are large numbers. I want to slow down here. When we say that the light from TON 618 takes 10.4 billion light-years to reach us, we are not saying that the object is 10.4 billion light-years away in any simple sense. The universe has been expanding the entire time the light has been travelling. The space between us and TON 618 has stretched. The object's actual present-day distance, in the sense of laying a ruler across the universe right now and reading the number, is the co-moving distance. That is 18.2 billion light-years, larger than the light travel time because while the light has been moving toward us, the space between has been getting larger. What we see when we look at TON 618 with a telescope is not the object as it is now. It is the object as it was 10.4 billion years ago. Hold that for a moment. The universe is presently estimated to be 13.8 billion years old. The light reaching our telescopes from TON 618 left when the universe was 3.4 billion years old, less than a quarter of its present age. What TON 618 looks like today, what it has been doing for the intervening 10 billion years, we will not see. Ever. The light has not reached us. It will, eventually. But by the time it does, all of us will have been dead for so long that the time span begins to lose meaning. What we have, what we measure, what we know about TON 618 is the photograph the universe took of itself 10 billion years ago. The quasar phase, the phase in which the disk is bright and the engine is active, and the object pours out its appalling luminosity, may not last forever. Quasars dim, black holes consume the gas reservoirs around them and grow quiet. By now, 10 billion years later, TON 618 may have grown into something larger. It may have grown quieter. It may, somewhere in its long history, have undergone mergers with other holes. Its disk may have dispersed. Its host galaxy may have collided with neighbours, or it may have settled into the gravitational drift of its local cluster. We do not know. We cannot know. The information has not arrived. We know it as it was. We do not know it as it is. This is one of the textures of looking at distant objects. They are, in a real sense, frozen at the moment their light departed. They cannot be updated. They cannot be checked. The catalogue entry is, in this sense, a historical record. The faint blue speck on the Tonantzintla plate is not a star. It is not a galaxy. It is a photograph of an event that occurred so long ago that the entire history of life on Earth has passed in the interim. And the event, the thing being photographed, was a region of space-time so curved that no signal could escape its central boundary. Stay with me here. This is one of the hard parts. The numbers are easy to recite. The implications, when we try to hold them at all, dislocate the body's sense of where we are. The mind reaches for the words and the words run out. Let us walk through what happened next. After Sandage flagged the object as a candidate quasi-stellar source, the work of pinning down the parameters began. Spectra were taken, redshifts measured, brightnesses tracked. The object was added to growing catalogues of distant quasars. The Sloan Digital Sky Survey, which began in 2000 and continues to this day, would eventually capture spectra of TON 618 with signal-to-noise ratios that the original Tonantzintla plate could not approach. In 2004, a team of researchers at Tel Aviv University, working with archival data and new spectroscopic measurements, applied the virial-method of black hole mass estimation to TON 618. The method is, in outline, simple. You measure the width of the emission lines from gas in the broadline region of the quasar. That width tells you how fast the gas is moving. You measure the luminosity of the disk. That tells you the size of the broadline region. Velocity times radius in the right combination gives mass. The number that came out of the calculation was 66 billion solar masses. The result was published in the Astrophysical Journal. The paper appeared in volume 614. It went through peer review. It was checked. It was cited. Other teams ran independent versions of the calculation. Some used different emission lines. Some used different assumptions about the geometry of the broadline region. Some came in higher. Some came in lower. The factor of 3 uncertainty inherent in the virial-method gave a possible range from 22 billion to 200 billion solar masses. The median was 66 billion. That is the number that has held, broadly, for the past 2 decades. Newer estimates with better data and improved modelling of the broadline region have not significantly changed the result. TON 618 remains the largest single black hole in any catalogue that has been compiled by any human astronomer. The runner-up, an object designated J2173602, measured by a team in Australia in 2020, came in at 34 billion solar masses. That is, by any other metric, an enormous black hole. But it is roughly half the mass of TON 618. There are candidate ultramassive black holes still under investigation. Mass estimates for some active galactic nuclei occasionally drift above 100 billion solar masses in preliminary work. Some of those estimates may, with refinement, settle higher. Some may settle lower. The field is active. But of the holes that have been measured, with the techniques we have and the data we have, TON 618 holds the record. And the record is the problem. Now, let us pull back and let us hold the problem. 66 billion solar masses at a redshift of 2.219 means that we are observing this object at a time when the universe was 3.3 billion years old. The standard cosmological model, what physicists call the lambda CDM model, gives us the rate at which black holes can grow under normal accretion physics. The growth limit is called the Eddington limit. The principle is straightforward. As matter falls toward a black hole, it heats up. It radiates. The radiation pushes outward on any further infalling material. There is a maximum rate at which a black hole can accrete before the outward radiation pressure begins to clear away the infalling fuel. That maximum rate is the Eddington limit. Under continuous Eddington-limited accretion, a black hole's mass grows exponentially, with a doubling time of roughly 45 million years. This is the math. A small black hole, say 100 solar masses, growing at the Eddington limit, doubles every 45 million years. After 1 billion years, it has doubled approximately 22 times. The mass increases by a factor of 4 million, so the 100 solar mass seed reaches 400 million solar masses in a billion years. To reach 66 billion solar masses from a 100 solar mass seed, you need approximately 30 doublings. That requires 1.3 billion years of continuous, uninterrupted, Eddington-limited accretion. If you start the clock at the moment of the Big Bang, you have 13.8 billion years of cosmic time total. TON 618 is observed at 3.3 billion years. That leaves 3.3 billion years for the black hole to grow. 3.3 billion years. For a stellar mass seed, you need at least 1.3 billion of those years just to reach the observed mass. That leaves 2 billion years for the seed to form, for the host galaxy to assemble, for star formation to occur, for the first stellar mass black holes to coalesce, and for the conditions of continuous Eddington-limited accretion to be established. The math is tight. Too tight. Let me bring that closer. The earliest galaxies in the universe, the ones we can detect with the James Webb Space Telescope, were already forming stars and clustering into protoclusters within the first few 100 million years after the Big Bang. The first black holes, if they formed from the collapse of the first generation of massive stars, would have started small. The conditions for continuous accretion at the maximum theoretical rate, sustained without interruption for over 1 billion years, are not naturally produced in any cosmological simulation we have run. What this means, in plain language, is that the standard growth model cannot produce TON 618 in the time available. The discrepancy is not subtle. It is not a factor of 2, it is structural. There are 3 possible resolutions that the field has proposed. None of them is fully established. All of them require us to extend, modify, or replace some part of the standard cosmological model. The first resolution is direct collapse. In this scenario, the black hole seed forms not from the collapse of a single massive star, but from the direct gravitational collapse of a vast cloud of pristine, atomic hydrogen, in a region of the early universe where conditions prevented the cloud from fragmenting into individual stars. The collapse forms a single black hole with a mass of perhaps 100,000 solar masses, or even 1 million, right from the start. If TON 618 began as a 1 million solar mass direct collapse seed, the math becomes easier. From a 1 million solar mass seed, you need only about 16 doublings to reach 66 billion. That requires roughly 700 million years of Eddington-limited accretion. The remaining time becomes manageable, but direct collapse requires specific conditions. The pristine cloud must be illuminated by ultraviolet radiation from neighbouring star-forming regions, hot enough to suppress molecular hydrogen formation, which would otherwise allow the cloud to cool and fragment. The conditions are plausible. The conditions have not been directly observed. The second resolution is super Eddington accretion. In this scenario, black holes in the early universe accreted faster than the standard Eddington limit by routing the infalling material through geometrically thick disks that radiated less efficiently. The infall continues. The radiation pressure is partially defeated. The growth proceeds at rates that the standard model forbids. Super Eddington accretion is observed in some local sources, particularly in ultraluminous X-ray binaries. Whether it can be sustained at the rates required to grow TON 618 in 3 billion years is an open question. The models permit it under certain conditions. The conditions again are plausible but not confirmed. The third resolution is mergers. In this scenario, multiple intermediate mass seeds form independently in the early universe, sink to the centre of a hierarchical assembly of dark matter halos, and merge into a single ultramassive object. The growth is hastened by adding seeds together rather than by accreting gas. The merger scenario is consistent with gravitational wave observations from LIGO and Virgo, which have detected stellar mass and intermediate mass black hole mergers. Whether the rate of such mergers in the early universe is sufficient to produce a 66 billion solar mass object by redshift 2 is again an open question. All 3 resolutions are partial. Most likely the true history of TON 618 involves elements of all 3, a direct collapse or merger-rich seed, followed by periods of super Eddington growth, followed by gradual settling into ordinary growth. The combined effect is enough to explain the mass. but each step, individually, requires extensions to the standard model that the field is still working through. Let me sit with the direct collapse picture for a moment, because it is, in my reading of the literature, the most likely answer. Imagine the universe at an age of 200 million years. The first generation of stars has just begun to form. The cosmic background, the leftover radiation from the Big Bang itself, is still relatively warm. The intergalactic medium is hot. Most of the hydrogen is still neutral. Galaxies are assembling, faint, partial, not yet recognizable as the structures we know from our own time. In this universe, there are vast clouds of primordial gas. The clouds are pristine. They contain only hydrogen and helium, with no metals to speak of. They are gathering under the pull of dark matter into the centers of forming halos. The question for the cloud is whether it will fragment. If the cloud fragments, it breaks up into many smaller pieces. Each piece collapses to form a star. The stars are massive, short-lived, and end as ordinary stellar mass black holes. This is the pathway that produces the bulk of stars in the universe. If the cloud does not fragment, something else happens. The whole cloud collapses as a single object, all at once, directly into a black hole. No stars, no supernovae, no chemical enrichment. Just one massive collapse. All the way through, for the cloud to avoid fragmentation, the gas must be unable to cool below a certain threshold. The standard cooling channel in pristine gas, at the temperatures of the early universe, is molecular hydrogen. The hydrogen atoms pair up. The molecules radiate away energy. The cloud cools. The cloud fragments. If, however, the cloud is bathed in ultraviolet radiation from a nearby region of star formation, the radiation dissociates the molecular hydrogen as quickly as it forms. The cooling channel is shut off. The cloud cannot cool below about 10,000 degrees Kelvin. At that temperature, gravitational collapse can proceed for the cloud as a whole, without fragmenting. The result after the collapse is a single object of perhaps 10,000 to 1 million solar masses, a direct collapse black hole. A seed. The seed grows from there by accretion, by mergers with other seeds, and with subsequent stellar mass holes, by the slow accumulation of mass over the next several billion years. If you start with a million solar mass seed at an age of 200 million years and grow at the Eddington limit for 2 billion years, you reach roughly 65 billion solar masses. The math works. The math works. The question is whether the conditions for direct collapse are common enough in the early universe to produce the population of ultramassive holes we see. The answer from current simulations is that the conditions are plausible. Whether they are common enough is still open. The picture is not settled. But the picture is becoming more capable of explaining what we see. Stay with me here. This is the part where the language of cosmology becomes most provisional. We have a story. The story has gaps. The gaps are being filled slowly by new observations and new models. The filling is the work. Now let us consider the super Eddington scenario in a little more detail. The Eddington limit, as I described earlier, comes from a balance between gravitational infall and radiation pressure. When matter falls toward a black hole, it heats up. The heat radiates outward. The radiation exerts a pressure on any further infalling material. At a certain rate of accretion, the outward pressure becomes large enough to push the infalling material away as fast as it tries to fall in. That rate is the Eddington limit. The limit, in standard derivation, assumes that the infall is roughly spherical and that the radiation escapes freely. If either of those assumptions breaks, the limit can be exceeded. Consider, for instance, the case where the infall is highly anisotropic. The material falls in along a thin disk. The radiation escapes preferentially along the disk's vertical axis, perpendicular to the inflow. In that geometry, the radiation pressure on the infall is much reduced. The disk can absorb more material per unit time than the standard Eddington limit allows. Alternatively, consider the case where the disk itself is geometrically thick. The material is dense enough that the photons cannot escape immediately. They are advected, carried along with the flow, into the hole itself. The radiation pressure is delivered to the hole rather than back to the inflow. The limit is, again, exceeded. Both of these geometries have been observed, at least in nearby systems. Ultraluminous X-ray binaries, observed in nearby galaxies, sometimes accrete at rates that imply super Eddington flows. The systems are local. They are well characterized. The physics is, to a first approximation, understood. Whether the same physics applies at the scale of the supermassive holes in the early universe is a question of geometry, environmental conditions, and duration. The conditions may be right in particular cases for super Eddington flows to be sustained for short periods. Whether they can be sustained for long enough to grow the holes we see is, again, open. Numerical simulations of early universe black hole growth, performed by various groups over the past decade, suggest that super Eddington flows are likely a significant contributor to the growth of the most massive seeds. The flows are episodic. The flows are concentrated in the densest regions of the early universe, where gas is abundant and merging halos provide repeated fuel. The picture, again, is consistent with what we observe in TON 618 and similar ultramassive objects. The picture is not yet quantitative enough to give precise predictions. The work is ongoing. The merger scenario is the third pillar. The picture there is straightforward in outline. In the early universe, the assembly of large structures is hierarchical. Small halos merge into larger halos. The black holes at the centers of merging halos eventually fall together and merge as well. Each merger increases the central black hole mass. The rate of mergers in the early universe was much higher than it is today. The galactic environments were denser, the encounters more frequent, the merger pairs more common. Each merger event adds mass to the central object. Over the course of 2 or 3 billion years, many such mergers can accumulate. If the typical seed is a few thousand solar masses, and the merger history involves dozens of significant events, then the cumulative mass after the merger history can reach into the tens of billions of solar masses. Even without much Eddington-limited accretion, the mergers themselves do most of the work. This scenario is consistent with the gravitational wave observations from LIGO and Virgo, which have detected stellar mass and intermediate mass black hole mergers. The frequency of supermassive mergers in the early universe can be inferred from these detections with appropriate scaling. The picture again is plausible. Whether the merger rate is high enough to produce TON 618 in particular is again an open question. Meantime, the likely answer involves all three pathways, each contributing some fraction of the total mass over the available time. The mass came from somewhere. The somewhere is not yet fully characterized. The work continues. Now let me bring that closer. What this picture means, in plain language, is that the most massive black holes in the universe were assembled through a combination of pathways that are not yet fully understood. The pathways are real. They produce real objects. We have measured the products. We are still working backward to figure out the assembly. This is, in some sense, the typical situation for any deep question in modern science. We have the answers. We have the products. What we are missing is the full history. The history is being reconstructed, piece by piece, through observation, simulation, and theory. The reconstruction is incomplete. The reconstruction will continue, and TON 618 sits as one of the most extreme cases at the boundary of what we have so far reconstructed. It is the upper edge. It is the prompt for further work. Now, the second part of why TON 618 breaks the universe, it is not just that it is too big for the time available, it is that its size, by any normal metric of what we consider a physical object, is greater than the scale of our solar system. The event horizon contains, within its boundary, more volume than the entire region of space that humans have ever directly probed with any instrument. Hold that. Voyager 1, after 47 years of continuous flight, has travelled approximately 25 billion kilometres. The event horizon of TON 618 is more than 200 billion kilometres in radius. The event horizon is more than 8 times farther out than Voyager has reached. If you began at one point inside the event horizon and started walking in a straight line at the speed of light, you would not reach the other side for approximately 3 weeks. That is, 3 weeks of continuous light speed travel just across the diameter of the boundary. For comparison, a photon takes 8 minutes and 20 seconds to travel from the Sun to the Earth. The event horizon of TON 618 is a region of space, defined by the gravity of the central object, that no light can cross in less than about 21 days. And here is the thing the physics demands. Inside that region, time and space behave differently than they do outside it. The geometry of the horizon is such that, once inside, the only direction available is toward the central singularity. There is no possible trajectory that returns the object to the universe outside. Every direction, every possible future world line leads inward. To escape the horizon, you would need to travel faster than light. The universe does not permit this. Anything that crosses the horizon is in the process of falling. The fall has a duration, in the rest frame of the falling object, of perhaps a few hours. In the case of TON 618, the fall ends at the central singularity, where the curvature of spacetime, in classical general relativity, becomes infinite. The classical theory breaks down at the singularity. What actually happens there is not known. Quantum gravity might tell us. Eventually. We do not yet have the answer, so inside this region, more than 200 billion kilometers in radius, every direction leads to a place we do not yet have the language to describe. Stay with me here. This is the second thing about TON 618 that, when we sit with it, does not quite fit the shape of any ordinary intuition. Now let us walk through the third. The third thing is what TON 618 implies about the population of similar objects. If we have measured a 66 billion solar mass black hole in a particular small corner of the sky in one specific direction of view, then by simple statistics there should be others. The universe is not homogeneous in detail, but on the largest scales it is roughly the same in every direction. What we see in one direction, we should, broadly, expect to see in others. The volume of the observable universe at redshift 2 is enormous. Roughly 2 billion luminous galaxies sit within that volume. Of those, perhaps 1% are believed to host an ultramassive black hole in the upper percentile of mass. That percentile, depending on which sample you choose, ranges from 1 billion solar masses upward. TON 618 is at the upper end of even that distribution. There may be others its size. There may be objects larger. The reason we do not know is because our methods of measurement are limited by what we can resolve, what we can detect, and what we have time and instrumentation to point at. The Sloan Digital Sky Survey has catalogued perhaps 1 million quasars in total. Of those, only the most distinctive few have had their masses determined to the accuracy that TON 618 has. The rest sit in databases awaiting follow-up. Some of those, when we get to them, will turn out to be larger than TON 618. This is not speculation. This is the result of doing the math on what the survey has captured versus what has been analysed in detail. The universe contains almost certainly ultramassive black holes that exceed 66 billion solar masses. We have not yet measured them because we have not yet had the resources to do the analysis at every candidate. The candidate list grows faster than the measurement list. The backlog stretches indefinitely. And yet, of all the candidates we have measured, TON 618 holds the record. The faint blue speck on the Tonantzintla plate from 1957 turned out, after 67 years of measurement and refinement, to be a region of spacetime so curved that its boundary alone is larger than our solar system, and so old that we will never see it as it is, only as it was. That is the first part of the story. There is more, and yet before we continue, I want us to pause for a moment. The numbers we have walked through have a particular texture. They are all verifiable. They are all derived from spectra that have been published, debated, and refined. They are not, in any sense, speculative. They are measurements. What is harder to hold is what the measurements imply. The implication is that the universe permits structures whose scale is on the order of our solar system, made not of matter that we can examine, but of curvature, pure geometry, a region of space that has folded inward, under the weight of its own contained mass, to the point that nothing can return. The universe permits this. The universe contains, by the latest count, at least one of these on a scale that defies the standard models we use to explain its history. And the universe contains us. And we have somehow, in the last few decades, built instruments capable of measuring all of this from a thin film of atmosphere on a small rocky planet that orbits a moderate star in a quiet arm of an ordinary galaxy 10 billion light-years from the object in question. This is the picture I want you to hold. We are not the centre. We are not the focus. We are not the addressee. We are the witness. That is a particular kind of position. Witness positions in the history of human inquiry are not common. Most cultures, most of the time, have placed themselves at the centre of their cosmologies. The sky was something that revolved around us, or that was watched over by powers that took an interest in us, or that was given to us, in some way, for our benefit. In the modern picture, none of that is true. The sky was not given. The sky was already here. We are the latecomers. And the things we are now finding, in the small corner of the constellations we have learned to read, were here long before us. They have been doing what they do. They have grown, dimmed, merged, settled, drifted apart. They have done all of this in the dark, with no audience, with no observer. For billions of years. What changed in our time is not that any of this began. What changed is that we built the instruments that allowed us, for the first time, to overhear what had always been happening. The faint blue speck on the Tonantzintla plate, captured in 1957, is a recording of an event that occurred 10 billion years before that plate was developed. The plate is, in a real sense, archaeological. It is a fragment of an older world, preserved in silver halide on glass, in a small dome at the foot of an extinct volcano in central Mexico. What we have done with that recording is to read it more carefully than its original cataloguers ever thought to do. We have measured what it contains, we have published, we have refined, and we have arrived eventually at a number that the standard model of cosmology cannot easily accommodate. The number is 66 billion. The unit is solar masses. The implication is that the universe permits structures whose scale and history exceed the descriptions we have so far prepared for them. Now let us continue. I want to spend some time now on what the inside of an event horizon is actually like, given what we know from general relativity. This is technical territory. I am going to walk through it slowly. The event horizon, as I mentioned, is a boundary in space-time. It is not a physical surface. There is no membrane there. If you were hypothetically falling toward Ton 618 from far away, you would not notice the horizon at the moment you crossed it. There would be no flash, no bump, no sensation of crossing anything. The space around you would look, locally, just like the space anywhere else. The horizon is defined globally. It is the boundary of the region from which no future-directed light ray can reach infinity. To know whether you are inside or outside the horizon, you need to know the global structure of the space-time. Locally, you cannot tell. What you would notice after crossing the horizon is that the central singularity is in your future. Not in your forward direction, in your time direction. You are falling toward it in the same sense that, outside, you fall toward next Tuesday. You cannot avoid it. You cannot reverse course. You can only watch your proper time tick down until the singularity arrives. For Ton 618, the proper time from horizon to singularity, for an object falling radially in from rest at the horizon, is on the order of several hours, depending on the precise trajectory. During those hours, the geometry around you would deform progressively. The radial direction would shorten. The tangential directions would lengthen. Tidal forces at the singularity itself would diverge to infinity. The infalling object would be stretched and compressed simultaneously in a process that the literature, for nearly half a century, has called spaghettification. For a supermassive hole like Ton 618, the tidal forces near the horizon itself are weak. An object the size of a human being could, in principle, cross the horizon without immediately noticing any deformation. The strong tidal effects come later, deeper inside, as the radial distance to the singularity shrinks. So you would have a few hours falling in a region of space whose geometry was at first almost normal. You would see the universe outside through a window that, gradually, would shrink and redshift. The cosmological clock outside would, from your perspective, accelerate. By the time you reach the singularity, billions of years of cosmic time would have elapsed in the universe outside. You would not survive to see what happened. The singularity ends the trajectory. The classical theory predicts your destruction. Quantum gravity may rewrite this part of the story. We do not yet know. Let me hold what the singularity is for a moment, because this is the place where the language of physics runs out. In classical general relativity, a singularity is a point where the curvature of space-time becomes infinite. The equations that describe the geometry of the universe yield divergences. Quantities that should be finite are not. The mathematics, in some sense, breaks down. This does not necessarily mean that the universe itself, at the singularity, contains an actual infinity. It means that the description we have, the description provided by general relativity, fails to give a sensible answer at that location. The failure is, in some sense, the prompt for a deeper theory. The deeper theory, which we do not yet have in finished form, is quantum gravity. The deeper theory should, in principle, smooth out the singularity, replace it with something finite, and give us a description of what is actually there. Various candidate theories of quantum gravity, including loop quantum gravity, string theory, and various proposals for emergent gravity, have offered tentative descriptions of what the singularity might be replaced by. Some proposals involve a region of extremely high but finite curvature. Others involve a transition into a different topology, perhaps a tunnel to another universe, perhaps a region of space-time that bounces back outward. None of these proposals has been confirmed. None has been refuted in any decisive way. The matter is open. For TON 618 specifically, the singularity at the centre, if it is a singularity, is shielded from outside view by the event horizon. We cannot observe it. We cannot test theories of what it is from outside. The horizon protects the inside from any possibility of remote inspection. This is, in the literature, called cosmic censorship. The conjecture, due to Roger Penrose in the 1960s, is that all singularities in classical general relativity are hidden behind event horizons. The universe, in some sense, refuses to expose its breakdowns to observers outside. Whether the conjecture is strictly true is still a matter of mathematical research. But for all the black holes we know, including TON 618, the horizon is in place. The singularity is hidden. What this means for TON 618 is that the central singularity, whatever it is unreachable to us. We can describe the horizon. We can describe the geometry just outside it. We cannot describe with any confidence what lies at the very centre. Inside that boundary, the universe contains something. Whatever the something is, it has been there for many billions of years. The boundary has held. The horizon has not evaporated. The singularity, if there is one, has not yet been resolved by any quantum mechanism we have access to. It sits there. It will sit there for a long time. The Hawking evaporation timescale for a black hole of 66 billion solar masses is, in standard calculations, on the order of 10 to the 100 years. That is a number so large that no language has been built to make it intuitive. It is many orders of magnitude longer than the current age of the universe. By the time TON 618 would, by Hawking radiation alone, return its mass to the surrounding spacetime, the rest of the universe will have undergone changes that would render the question of its return moot. So TON 618 is, in any practical sense, eternal. It is, for the foreseeable future of the universe, going to be there. It is, for the foreseeable future of our cosmological era, going to be one of the largest individual gravitating structures in existence. That is a long timescale. It exceeds the timescale of every other phenomenon we will discuss tonight, with the possible exception of the very end of cosmological evolution itself. Now, stay with me here. There is a particular kind of vertigo that comes from sitting with these scales. The vertigo is not, I think, about danger. It is not about threat. It is about the simple fact that the universe contains structures whose duration so far exceeds our own lifetimes, whose extent so far exceeds our own region, and whose internal physics so far exceeds our current ability to describe, that we are reduced, when we look at them, to the role of distant observer. The role of observer is a particular one. It is not a role of participant. It is not a role of consequence. The black hole does not change in any meaningful way because we are looking at it. The black hole continues to do what it does. Our observations are recorded on Earth. The black hole does not register our recordings. The black hole does not register us at all. We are looking. We are recording. We are not, in any way, part of the system we are looking at. This is not, I want to be clear, a pessimistic point. It is a clarifying one. Our position in the cosmos is unusual. Our planet is rare. Our species is rarer. The fact that we have built the instruments to see these things, and the institutions to interpret them, and the patience to do the work over the course of decades is the unusual part. The black hole is ordinary. We are the strange one. We are the strange one because we are the witness. The witness is, in the long history of the universe, a recent development. There were no witnesses for most of the history of the universe. The universe ran its first 13 billion years without anyone watching. Stars formed, galaxies assembled, black holes grew. Quasars burned and dimmed. Cosmic webs evolved. Dark matter halos clustered. None of this was watched. None of this was recorded. Now, in the last small fraction of cosmic history, a watcher has appeared. The watcher is us. The watcher has built instruments. The watcher has begun to record. What the Watcher records is, in some sense, the late history of a universe that ran most of its course without observers. TON 618 is a record of an event from that long unwatched period. The light from the event has only reached us now, after a journey of 10 billion years. We are the first observers, anywhere we know about, to receive that light. We are reading the message. The message was not addressed to us. The message was simply released into the universe by the physics of an active accretion disk in a particular small region of space, 10 billion years ago. We are reading it. We are the audience. That is the texture of what is happening tonight. Let me hold one more thing before we move on. The fact that the message arrives at all is itself notable. The light from TON 618, after travelling 10 billion years through the expanding universe, arrives at our telescopes with a particular wavelength, redshifted by the expansion, but otherwise intact. The photons that left the disk all those years ago, individual photons, particular quanta of light, are the same ones we capture. They have not, in any meaningful sense, decayed. They have not lost their identity. They are, in the technical sense, the very same photons. This is one of the small wonders of optics. The photon is stable. It travels indefinitely. As long as nothing intercepts it, it continues through the cosmic dust, through the intergalactic gas, through the expansion of space, through the redshift. The photon persists. What we see when we look at TON 618 is a faint flux of photons, each one of which left the disk a long time ago, each one of which has been on its solitary journey ever since, and each one of which has, by virtue of arriving at our particular telescope, at this particular moment, ended its journey here. The journey ended at our detector. The journey began at the disk. The duration was 10 billion years. We can, in principle, count those photons. We can measure their wavelengths. We can extract from them the information they carry about the source. That is the work of spectroscopy. The work has been done. The work continues. Each photon is a small messenger. Each carries a small fraction of the information about the source. Many photons summed together give us the spectrum. The spectrum, interpreted, gives us the mass. The mass is 66 billion solar masses. The number is the result of decades of careful work, with photons that have been in transit for 10 billion years. This is what we have done. But the inside of the horizon, for the few hours you would spend in it, is a region of space-time that the universe permits, that we have characterized mathematically, and that, for TON 618, is on a scale that exceeds the dimensions of our solar system. This is what I mean when I say that the universe is not what we expected. For most of human history, we did not know that black holes existed. The idea was first proposed in mathematical form in 1916 by Carl Schwarzschild, who derived the solution to Einstein's field equations for a non-rotating point mass. Schwarzschild's solution contained, at a particular radius, what was then called a coordinate singularity. The radius is what we now call the Schwarzschild radius. The boundary at that radius is the event horizon. For several decades, the physics community was uncertain whether the Schwarzschild solution represented a real physical object or a mathematical artifact. The matter was settled, by stages, over the course of the 20th century. Observations of compact binary systems in the 1970s, followed by stellar dynamics at the centre of the Milky Way in the 1990s and 2000s, and ultimately by the Event Horizon Telescope imaging in 2019, established beyond reasonable doubt that black holes are not just mathematical objects. They are physical, and once that was established, the field had to confront the question of how big they could get. Stellar mass black holes are produced by the collapse of massive stars. The mass of the stellar core at the end of fusion sets the mass of the resulting black hole. The range is roughly 5 to 100 solar masses for objects formed from individual stars. Above that, in the intermediate mass range, the production mechanisms are less certain. Some intermediate mass holes may form in dense stellar clusters by repeated mergers of smaller objects. Above 10,000 solar masses, we enter the supermassive class, found at the centres of most large galaxies. Production mechanisms include direct collapse, runaway accretion in the early universe, and successive mergers over cosmic time. Above 1 billion solar masses, we enter the ultramassive class. Production mechanisms here are not fully understood. The standard model of cosmological growth, as I have walked through, has difficulty producing objects of this size in the time available since the Big Bang. TON 618 sits at the upper end of the ultramassive class. 66 billion solar masses, possibly larger when uncertainty is included. It is the largest catalogued. This is the territory we are in. This is what the universe contains. Now let us pull back. We have walked through what TON 618 is, how big, how far, how old, and how it is measured. We have walked through why its size is, by the standards of cosmological growth models, difficult to explain. We have walked through what the inside of its event horizon looks like in the geometry of general relativity. There is more to say. There is the question of the host galaxy. There is the question of jets. There is the question of what the object is doing now, 10 billion years after the light we see was emitted. There is the question of what other objects, in other directions, may be similar or larger. And there is the question, more philosophical than physical, of what it means to have inhabitants of a small planet, in a small star system, in a small region of a galaxy, measure an object whose mass exceeds the mass of every star in every galaxy, within 100 million light years of itself, all combined. I want to walk through each of those slowly, in turn, and then I want to come back, near the end of this walk together, to the faint blue speck on the photographic plate, in the small dome on the slopes of an extinct volcano in central Mexico, in 1957. Because the faint blue speck is still there, it is still there in the archive. The plate has been preserved, the catalogue is still consulted. And the small numerical designation, 618, given to the speck by a clerical hand on a Tuesday afternoon, in the year before Sputnik was launched, is the only name by which the object is widely known. We did not know what it was. We catalogued it anyway. That is what the work looks like. That is what the work has always looked like. The universe shows us what it has. We record what we can. If offiziell, we do not always understand what we have recorded. The understanding comes later, in stages, by the work of many hands across many decades. That is the texture of what we are doing here tonight. We are walking through one such record, one such object, one such number. The number is 66 billion. The implication, when we sit with it, is that the universe permits more than we have so far written down in our books of how it works. And we have only been looking, in the careful, detailed way, for a few centuries. There is a great deal still to come. Now let us turn to the host galaxy of TON 618. The black hole, as enormous as it is, sits at the centre of a galaxy. The galaxy is not bright enough to be easily seen against the brilliance of the quasar at its core. The disk of the black hole outshines its host. To detect the host, astronomers have to subtract the point source of the quasar from the images and look at what remains. The remainder is the galaxy. The work has been done. The host is what astronomers call an ultra-luminous infrared galaxy, of the type that, in the early universe, was producing stars at extraordinary rates. The galaxy is forming stars perhaps 1,000 to 10,000 times faster than our own Milky Way is doing today. The dust is heated by the starbursts. The dust radiates in the infrared. The host appears, when separated from its quasar, as a hot, dusty, vigorously forming object. The relationship between the central black hole and the host galaxy is one of the central questions of modern cosmology. Black holes do not just sit passively at galactic centres. They appear to grow alongside their hosts, with the mass of the central hole correlating with the mass of the galaxy's stellar bulge in a very tight relationship. The correlation, called the M-sigma relation, suggests that the growth of the black hole and the growth of the galaxy are linked. Either the galaxy regulates the hole, or the hole regulates the galaxy, or some feedback mechanism between them produces the observed correlation. In the case of TON 618, the relationship is extreme on both ends. The hole is the largest catalogued. The host is among the brightest infrared galaxies known at its redshift. The pair are unusual. The pair represent, in some sense, an extreme of what the early universe was capable of producing. The growth in the period when the light we see was being emitted was rapid on both ends. The hole was accreting at high rates. The host was forming stars at high rates. Each fed the other, in some sense. The dust and gas falling into the centre of the galaxy fed the hole. The radiation from the hole, in turn, pushed gas around the galaxy, heating it, perhaps shutting off star formation in places, perhaps triggering it in others. By now, 10 billion years later, the host has almost certainly evolved into a different kind of object. The starburst would have ended. The hole would have entered a quieter phase. The disk would have dimmed. the galaxy would have settled into the form of a massive elliptical, with most of its stars old and red. This is the typical fate of these objects. The bright quasar phase is brief cosmically speaking. It lasts perhaps 100 million years on and off. After it ends, what remains is a dormant, supermassive hole at the centre of a quiet old galaxy. Most of the supermassive holes we have catalogued in our local universe are in this state. They are quiet. They are not producing quasars. They sit at the centres of massive ellipticals, or in the bulges of spirals, doing very little. What we see in TON 618 is the quasar in full activity, the full bright phase, the starburst still ongoing, the hole still actively accreting, the whole apparatus running at maximum output. What we are looking at, in essence, is one of the most extreme moments in the history of any single object the universe contains, frozen at the moment its light departed, and arriving at our telescopes 10 billion years later for us to inspect. It is a postcard from a particular moment in cosmic history. The postcard is, by virtue of distance, all we will ever see of that moment. The object that sent the postcard is presumably no longer doing what it was doing then. But we have the postcard. We have what the universe sent us. And we are still, 6 decades after the original photograph, reading it more carefully. This is what the work looks like. Now let us pull back and let us walk through the jets. The accretion disk of TON 618, like the accretion disks of most active quasars, is threaded with magnetic fields. The fields are dragged along with the infalling plasma. The fields are wound up, twisted, and amplified by the rotation of the disk. Near the central hole, the fields become extraordinarily strong, and they channel material away from the disk in 2 narrow streams, perpendicular to the disk plane. These streams are the jets. The jets of quasars, in general, can extend across hundreds of thousands of light years. They consist of relativistic plasma, moving at speeds close to the speed of light. They emit radiation across the electromagnetic spectrum from radio to gamma rays. They punch out of the host galaxy into the surrounding intergalactic medium and produce vast clouds of plasma that eventually slow and spread out and merge with the cosmic web. For TON 618 specifically, the jets are difficult to observe at the distance we have. The radio emission is detectable. The morphology is not fully resolved. What we can say is that the jets are there, that they are powerful, and that they are part of the system. They contribute to the energy budget. They redistribute material across the host galaxy and beyond. They are part of what makes the quasar what it is. Let me bring the jet physics a little closer, because the jets, when we sit with them, are a remarkable phenomenon in their own right. A black hole by itself has no electromagnetic field. The hole is defined by its mass, its spin, and its electric charge. In any natural astrophysical situation, the charge is essentially zero, because the surrounding plasma neutralizes any excess. What remains is mass and spin. The mass produces the gravitational field. The spin, if present, produces a frame-dragging effect on the surrounding spacetime. The frame dragging causes the local inertial frames to be rotated in the immediate vicinity of the horizon. The rotation extends outward, weakening with distance but still present. If a magnetic field is present in the surrounding plasma, the frame dragging twists the field lines. The twist accumulates. The lines become wound up around the rotation axis of the hole. The wound-up lines store enormous magnetic energy. The energy can be released in collimated outflows along the rotation axis. These are the jets. The process is called the Blandford-Znajek mechanism, after the 2 physicists who worked out the geometry in the 1970s. The mechanism extracts energy from the rotation of the hole itself, mediated by the magnetic field, and channels it into the relativistic outflow. For ultramassive black holes like TON 618, the jets can be extraordinarily powerful. The available rotational energy of the hole, in principle, is on the order of the total mass energy, multiplied by a fraction set by the spin. For a maximally spinning hole, the available energy is about 30% of the total mass energy. For a hole of 66 billion solar masses, that is an energy reservoir of roughly 20 billion solar masses, in pure energy units, vastly larger than anything achievable through accretion alone. Whether TON 618 is, in fact, near maximally spinning is not known. The spin parameter is difficult to measure for high redshift objects. The general expectation, from simulations of how supermassive black holes evolve, is that they tend toward intermediate or high spin values, because the accretion through a stable disk tends to spin them up. If TON 618 is highly spinning, the jets are drawing on the rotational reservoir, and the energy can be sustained for very long periods. The jets we observe are merely the visible portion of the outflow. The full extent, including the lobes and the cosmic web-scale impact of the jets on the surrounding intergalactic medium, may extend across millions of light-years. The jets in this picture are not merely a side effect. They are a major mechanism of energy transport from the central engine into the broader universe. They redistribute material, heat the intergalactic medium, and influence the chemistry of the cosmic web. Over cosmic time, the cumulative effect of all the jets from all the active galactic nuclei in the universe has shaped the large-scale environment in which galaxies form and evolve. TON 618 is one of those engines. Its jets over the few hundred million years that the quasar phase lasts would have done their share of the work. They would have heated their part of the cosmic web. They would have left their lobes in the surrounding intergalactic medium. The traces would have lasted for millions of years before fading into the broader cosmological background. What we observe today in the radio band is the residual signature of those jets. We see a small portion. The full picture, again, is partial. The reconstruction is ongoing. The jets, by some estimates, carry a fraction of the total energy budget of the accreting whole. The jets are, in a sense, the visible exhaust of the engine. They tell us that the engine is running. They tell us that the system is alive and active. The jets have done their work for hundreds of thousands, possibly millions, of years by the time the light we see was emitted. They have shaped the intergalactic environment around the host. They have heated the cosmic web. They have done all of this in the dark, and the consequences are still propagating outward, even as the light from the engine itself has been arriving at us. By now, 10 billion years later, the jets may have ended. The whole may have quieted. The galaxy may have settled. The cosmic environment around TON 618 presumably has continued its ordinary evolution. But we will not see it. Now let us walk briefly through what we know about how the disk produces the light we measure. The disk, in essence, is a flat structure of plasma orbiting the central hole. The plasma is governed by general relativity in the inner regions, where the gravitational field is strong, and by ordinary fluid dynamics in the outer regions, where the field is weaker. The orbits are roughly Keplerian in the outer disk, modifying to relativistic forms close to the hole. The temperature of the disk at any given radius depends on the rate at which mass is being deposited there and on the local efficiency of radiation. For TON 618, the disk is hot. Near the inner edge, where the plasma is closest to the hole, the temperature is on the order of 100,000 degrees Kelvin. Further out, the temperature drops with distance, roughly as the radius to the -3/4 power. The disk emits across a broad range of wavelengths, with the peak in the ultraviolet for an object of this mass and accretion rate. The integrated luminosity of the disk, summed over all wavelengths, is what we measure. The number is roughly 4 × 10 to the 40th watts. That is the bolometric luminosity. The number, for context, is roughly the combined output of 140 trillion suns. Where does this energy come from? The energy comes from the gravitational binding of the infalling material. As mass falls toward the hole, it converts its gravitational potential energy into kinetic energy. The kinetic energy in the disk is converted into thermal energy through friction. The thermal energy radiates away as light. The efficiency of this conversion in a standard thin accretion disk is on the order of 10%. That is, 10% of the rest mass energy of the infalling material is converted to radiation. The remaining 90% goes into the hole as additional mass. To produce the luminosity of TON 618, the hole must be accreting at a rate of perhaps several hundred solar masses per year, in continuous flow. The accretion has been ongoing, presumably, for as long as the quasar phase has lasted. Over the typical quasar duration of 1 to 200 million years, this rate would add tens of billions of solar masses to the central hole, consistent with the hole growing over its quasar lifetime to its present measured mass. The accretion is fueled by the host galaxy. The galaxy provides the gas. The gas spirals inward through the disk toward the hole. The host star formation, also fed by the same gas reservoir, occurs in parallel. The two processes, accretion and star formation, share the same fuel. When the fuel runs out, both processes end. The quasar phase concludes. The host settles into a quieter state. The hole stops growing rapidly. The disk dims. For TON 618, the quasar phase is presumably still ongoing in our view of the object. The light reaching us shows the system in the middle of its bright period. By now, 10 billion years later, the phase has almost certainly ended. The hole sits presumably in a dormant state at the centre of an evolved elliptical galaxy. The disk is dim. The jets have ceased. The system has settled. This is the typical fate. This is what happens eventually to all of the quasars we see in the high redshift universe. They burn brightly. They consume their fuel. They settle. They become the dormant supermassive holes that we see in the local universe. The remnant masses are what we measure today in nearby galaxies. The growth happened long ago. In the bright phase ended. The remnants persist. Now, let us hold the philosophy for a moment. The faint blue speck on the Tonantzintla plate in 1957 was a record of an event that the universe permitted itself, in a small corner of itself, 10 billion years before. The event was the active accretion of a black hole already too massive for the time available. The event was the radiation of an engine, threaded through a galaxy, throwing out jets and heating dust and pouring out light. The event lasted, in some sense, only as long as the engine was active. The engine has, by now, presumably ceased, but the record of the engine, the photograph it took of itself by emitting light into the universe, is still arriving. The light in the form of the faint blue point we still catalogue as TON 618 is still reaching our telescopes. What we are doing when we look at it is reading a recording that the universe made of itself a long time ago. The recording was not made for us. We were not the intended audience, we are not the addressee, but we have built the instruments, we have done the spectra, we have computed the redshifts, we have applied the virial-method, we have published the papers, we have done the work, and we have arrived on a particular small rocky planet at a number that the standard model of cosmology, the model we use to explain how the universe grew from its hot, dense beginning to its present cool and expanding state, cannot easily produce. The number is 66 billion. The unit is solar masses. The object is in Canes Venatici. The light is from 10 billion years ago. We have built our model of the universe carefully over the course of more than a century. The model works. It explains an enormous amount of what we see. It is the most successful description of the cosmos that any species, anywhere we know about, has produced. And the model has trouble producing TON 618 in the time it has available. The discrepancy is not, in any sense, fatal. The model will be refined. It always has been. New mechanisms will be added. The story will accommodate the data. That is how the work proceeds. But the discrepancy is a marker. It tells us that we have not yet finished the model. It tells us that the universe contains structures that we have not yet fully accounted for. It tells us that there is more to write down. This is, in some sense, the most reassuring thing the discrepancy can mean. We are not done. There is more to find. There is more to write down. The work is ongoing. That is the texture of what we are looking at when we look at TON 618. Now let me bring this part of the story to a slow close, and we will take a small pause before continuing into the deeper consequences. The faint blue speck on the Tonantzintla plate is still there. The catalogue is still consulted. The object is still observed periodically by survey instruments. The Sloan Digital Sky Survey has its spectrum on file. The James Webb Space Telescope, although not yet pointed at TON 618 in any dedicated program that has produced public data as of the last update, may, in future years, capture the object in its detailed infrared spectroscopy. New mass estimates may emerge. New constraints on the host galaxy may emerge. The story will continue. What we have at this moment is the number 66 billion, the redshift 2.219, the distance 10.4 billion light-years light travel, and the implication that the universe permits structures of this scale at this point in its history. That is what we have. That is what we are walking through tonight. We have time. There is more to come. Now let us turn for a while to the deeper implications of what TON 618 means for our picture of the universe at large. The universe in the picture we have constructed over the last century began in a hot, dense state approximately 13.8 billion years ago. The early universe was filled with hydrogen and helium, in the proportions set by primordial nucleosynthesis. Heavier elements, the carbon and oxygen and iron of which planets and bodies are made, did not yet exist. The first generation of stars formed from the primordial gas, perhaps a few 100 million years after the Big Bang. Those first stars were massive, short-lived, and metal-free. They produced the first heavy elements when they exploded as supernovae and dispersed their cores into the surrounding gas. Subsequent generations of stars formed from the chemically enriched material. Galaxies assembled by the gravitational pull of dark matter halos. Stars clustered. Disks formed. The universe gradually built up its present structure. Black holes in the picture formed from the death of the most massive stars. The first stellar mass holes appeared early. They grew slowly. They merged occasionally. They sat at the centers of forming galaxies. They accreted gas. They became, by the time of the first quasars, the engines of those quasars. The picture works broadly for objects of moderate size. It works for the supermassive holes at the centers of nearby galaxies like Sagittarius A star and M87. The masses observed at present can be explained with reasonable accuracy by the growth pathways the model allows. The picture works less well for the extreme objects. The picture works less well for TON 618. What TON 618 is, in the context of the standard model, is an outlier, an object whose mass exceeds the expected upper bound at its redshift, an object whose growth requires either a much larger seed than stellar collapse can provide, or a much faster growth rate than Eddington-limited accretion allows, or a much higher merger rate than the typical galaxy assembly produces. This is not, by itself, a problem for the model. Outliers are expected. Probability distributions have tails. Rare events occur. The model can absorb a single outlier without breaking. But TON 618 is not in fact the only such outlier. There is a growing population of high-mass black holes observed at high redshift. The James Webb Space Telescope, in its early observations of the most distant galaxies, has found black holes at redshifts of 7 and higher, at masses of hundreds of millions to billions of solar masses. These objects exist only a few 100 million years after the Big Bang. Their masses are difficult to produce in the time available. The pattern is consistent. Wherever we look in the early universe, we find black holes that are larger than the standard growth model can easily produce in the time available. This is not, I want to be clear, a crisis for cosmology. The model is being refined. Direct collapse seeds, super Eddington accretion, and rapid merger pathways are all being added to the standard picture. The story is becoming richer. The model is becoming more capable of producing the observed population. But the refinement is ongoing. We have not, as of this recording, settled the question of how the most massive black holes in the early universe came to be as large as they are. TON 618 is the most extreme example of this puzzle. 66 billion solar masses at a redshift of 2.2, larger than any other measured, sitting in our catalogues for nearly 7 decades, holding its title. What the title represents is the upper edge of what we currently know how to measure. The universe almost certainly contains larger objects. We have not yet caught them. We will in time. The work continues. Now, let us hold the small geometry of all of this. The Earth orbits a single star in a quiet arm of an ordinary galaxy. The galaxy contains roughly 200 billion stars and a single supermassive black hole at its centre. Of mass 4.3 million solar masses. That is the local geometry. Beyond the galaxy, in a sphere of roughly 10 million light-years, we find a few dozen larger galaxies and several thousand smaller ones. Each large galaxy hosts its own central black hole. The masses range from millions to billions of solar masses. MA87, the largest galaxy in our local supercluster, hosts a black hole of 6.5 billion solar masses. That is the largest local example. Beyond the local supercluster, the universe extends in all directions, sprinkled with galaxy clusters and superclusters, threaded by the cosmic web of dark matter and gas. The structure is large but finite. The observable universe extends, in light travel terms, to 13.8 billion light-years in every direction. The comoving distance is larger, perhaps 46 billion light-years on a side. TON 618 sits inside that observable volume, at a comoving distance of 18.2 billion light-years. Well within the bounds of what we can see, far enough, however, that the light has been travelling for most of cosmic history. Within the observable volume, there are perhaps 200 billion galaxies. Each hosts a central black hole, with masses set by the host size. The largest of these holes, the ones in the most massive galaxies, the ones at the high mass tail of the distribution, are what we call the ultramassive class. TON 618 sits at the top of that distribution by current measurement. The total mass of all the supermassive and ultramassive black holes in the observable universe, summed together, is on the order of 100 million times the mass of TON 618. That is, in terms of total black hole mass, TON 618 is 1 part in 100 million of the cosmic budget. But in any single direction we look, in any single small patch of sky, TON 618 is the largest individual we have measured. This is a particular kind of fact. The universe contains, in total, many times the mass of TON 618 distributed across countless similar objects. But our resolution is limited. We can only measure the holes we can pick out, the brightest, the closest, the most studied. Among those, TON 618 is the record holder. The record may fall. Surveys are ongoing, new estimates are emerging. In a decade or two, perhaps less, a larger object may be confirmed. The title will pass, but for the moment the record stands. That is where we are. Now, the question of jets again. More briefly, the jets of TON 618 are not, as far as we can tell, the most powerful jets in the known universe. There are other quasars with larger, brighter, more extensive jets. The jets of TON 618 are average for an object of its class. They are detectable. They are measurable. They are not record-setting. This is interesting in its own right. The largest hole does not produce the most extreme jets. The jet power depends on many factors: the spin of the hole, the magnetic field configuration, the accretion geometry. TON 618's jets are not unusual on any of these axes. The hole is enormous, its jets are ordinary. What is unusual about TON 618 is the central mass. Everything else about it is, broadly, average for an object of its luminosity class. The disk is bright. The jets are present. The host is a vigorous starburst. None of these is, in itself, unique. The unique aspect is the mass at the centre. That mass, when we sit with it, is the thing the universe is not supposed to permit at this point in its history. And yet the universe has permitted it. We have measured it. The number is settled. Now let us turn briefly to what comes next. The Vera-Rubin Observatory in Chile, currently in commissioning, will begin its full 10-year sky survey in 2026. The survey will image the entire southern sky every 3 nights, at depths far exceeding any previous wide-field survey. The survey is expected to find, among many other things, a vast population of quasars at high redshifts. Some of those quasars will, almost certainly, host black holes more massive than TON 618. The James Webb Space Telescope, already operating, has begun the systematic spectroscopy of high redshift quasars. Some of those spectra will yield new mass estimates that may, in time, displace TON 618 from its record position. The square kilometre array, currently in early science operations, will eventually map the radio sky at depths and resolutions that will reveal the jet morphologies of distant quasars in unprecedented detail. The data will refine our understanding of the jet physics of ultramassive black holes. The Athena X-ray Observatory, planned for the next decade, will measure the X-ray spectra of accretion disks at high redshift, providing independent constraints on black hole masses and growth histories. All of these efforts, when they come online and produce data, will deepen our picture of the ultramassive black hole population. The picture will become more nuanced, the growth pathways will become clearer, the exceptions will be more carefully characterized. But for now, in the present moment, in the catalogue as we have it, TON 618 holds its title. It does so quietly in a corner of Canes Venatici on a photographic plate from 1957 that has been read, reread, and remeasured for 67 years. The plate is still archived. The catalogue entry is still consulted. The number 66 billion still appears in the literature. And the light from the object, the actual photons that left the disk 10 billion years ago, is still arriving. They will continue arriving faintly, for as long as our instruments are pointed at that small patch of sky. The flow will not, in any meaningful sense, stop. There are more photons in transit. They are still in flight. They will eventually arrive. This is one of the textures of the work. The signal is continuous. The arrival is endless for as long as we look. The instrument is the limit. The signal is, in some sense, infinite. It is at any rate far larger than anything we can collect in a single observation. What we have is what we have collected. The collection is partial. The signal is more. The signal is older. The signal carries information we have not yet extracted. The collection continues. Now let us turn to the philosophical part of the story, briefly. What it means to know about TON 618 is, in some sense, what it has always meant to know about the cosmos. We are looking at something far away, large, ancient, and not particularly addressed to us. The thing is doing what things of its kind do. The thing has been doing this for a long time. We have arrived in our small corner to catch the last of the light. This is not new. This is what the work has always been. What is new is the scale. The Tonantzintla plate, in 1957, did not know that it was photographing a 66 billion solar mass black hole. The catalogue entry, when it was written, did not know either. The understanding came in stages over the course of decades, as the field of cosmology grew up around the data. What this means is that the data we collect now, with the instruments we have now, will, in some sense, be reread by future generations of researchers, with tools we have not yet built. The data we are storing, in the form of survey databases and digital spectra and archived images, will be the substrate on which future understandings of the universe will be built. This is one of the quiet aspects of the work. The work is cumulative. The data is preserved. The understanding compounds. Each generation adds its measurements. The next generation extracts what the previous generation did not have the tools to see. TON 618 is, in that sense, a small example of the larger pattern. A plate from 1957, a catalogue entry of one line, a subsequent identification as quasi-stellar, a spectrum, a redshift, a mass estimate, a discrepancy with the standard model, a growing population of similar objects in subsequent surveys, a continuing investigation. The work continues across generations. The plate remains in the archive. The catalogue remains consulted. The next set of measurements builds on the previous. The picture refines. This is what science looks like when we look at it across decades. It is slow. It is incremental. It is cumulative. And it does eventually produce results. Let me sit with that pace for a moment. 67 years, from the plate to the present measurement. That is the lifetime of an ordinary career, twice over. The plate, on the evening it was exposed, sat in a dark room while the rest of the world turned. The plate did not know what it contained. The astronomers who developed it did not know either. The catalogue card was written. The card went into a drawer. Other cards were written. The work moved on. 8 years later, Sandage made the identification. Another decade after that, the redshift was measured. Decades after that, the mass was determined. Each step took years. Each step required new instruments, new techniques, new generations of researchers, familiar with the prior work and capable of pushing it further. The pace, by the standards of most human activity, is slow. But it is the natural pace of cosmology. The signals we are reading are faint. The objects are distant. The phenomena are rare. The work takes time. And the work, when it is done, produces results that last. The number 66 billion has been in the literature for 2 decades now. It has been cross-checked, refined, debated, reconfirmed. It is, by current standards, a well-established measurement. It will not, in any plausible sense, be revised by more than the factor of 3 uncertainty inherent in the method. The number is what it is. The work has settled. That is the result of patient measurement. That is the result of long-term institutional effort. That is the result of the slow, careful accretion of knowledge across human generations. We are the beneficiaries of that accretion. We are reading the result. We are, in some sense, the witnesses of what previous witnesses have established. This is the work. This is what it has always been. The results in the case of TON 618 are these: a faint blue speck, catalogued in 1957, identified as a quasar, measured to be 10 billion light-years away, mass estimated at 66 billion solar masses, the largest single black hole in the catalogues, larger than the standard model can easily produce. A puzzle, a prompt for further work. The puzzle is, at this moment, in our hands. We are turning it over. We are looking at it from different angles. We are not yet sure what to make of it. We will continue to be unsure for some time. That is the texture of what we are doing tonight. Hold this. The puzzle, in the end, is not whether the object exists. The object exists. The measurement has been done. The data is settled. The puzzle is how the object came to exist on the timescale the universe has had available. The standard model of cosmology, as I have walked through, has 13.8 billion years from the Big Bang to the present. TON 618 was already this size at 3.3 billion years. The growth had to happen in the first quarter of cosmic time. The growth pathways permitted by the standard model, in their unmodified forms, do not deliver this growth, so the model must be extended. The extensions are being worked through. The work involves new physics, new mechanisms, new conditions in the early universe. The work is not finished. This is perhaps the most important thing I want to leave you with. Our picture of the universe is not finished. It is being written. The most extreme objects, the ones that sit at the edge of what we have so far described, are the prompts that drive the next iteration of the writing. TON 618 is one such prompt. It sits, faint and ancient, in its corner of Canes Venatici, demanding that our picture grow up to include it. The picture is growing up, slowly the way pictures do, by accretion across decades, with the help of new instruments and new minds. The work again continues. Now let me pull back, fellow night watcher. We have walked through the discovery. We have walked through the measurement. We have walked through the geometry. We have walked through the growth puzzle. We have walked through the implications for the broader population. We have walked through the host. We have walked through the jets. There is one more thing I want to come back to before we draw this evening to a close, but first, let me hold the implication for our local situation. We live in a galaxy. Our galaxy hosts a supermassive black hole at its centre. The hole is Sagittarius A star. The mass, as I mentioned, is 4.3 million solar masses. Compared to TON 618, our central hole is a small object, roughly 15,000 times smaller. What this means in practical terms is that our galaxy is not, and has never been, the host of a quasar of the brightness of TON 618. Our central hole is, in the language of the field, undermassive for our galaxy's stellar mass. The M-sigma relation predicts a somewhat larger central hole for a galaxy of our size. We have less than the relation expects. This is not necessarily a problem. The relation is a statistical average. Individual galaxies scatter around it. Our galaxy happens to scatter on the low side. What it means, however, is that our galaxy's central hole is, by the standards of the broader population, modest. It is not a record holder. It is not a notable object on the cosmic stage. It is one supermassive hole among the many 100 billion that the universe contains. The hole at our centre is, at present, also quiet. It does not produce a quasar. It does not emit relativistic jets that we can detect. It is in the dormant phase, accreting only a trickle of material, radiating mildly, doing very little of cosmological consequence. This may not always have been the case. There is some evidence from the structure of the gas in our central few hundred light years and from the so-called Fermi bubbles that extend many thousands of light years above and below the galactic plane, that our central hole was much more active in the past. Perhaps a few million years ago, perhaps tens of millions of years ago, our hole underwent a brief active phase. The phase produced the bubbles. The phase has since ended. The hole has returned to its quiet state. This is the normal cycle for a supermassive black hole, most of the time dormant, occasionally active. The total time spent active over the age of the galaxy is probably less than a few percent. TON 618, however, is in the bright phase. It is in the active period. It is doing what most supermassive holes spend most of their lives not doing. It is at the peak of its output. What we see in the photographic record is one of those rare bright moments. The moment is long, by human standards, hundreds of millions of years, but it is a small fraction of the total life of the host system. We are looking at the system during its peak. The peak ended, presumably, many billions of years ago. The peak left its remnant. The remnant persists. Now let me come back to the speck. I want to come back to the faint blue speck. Because the speck is still there, the plate is still archived. The catalogue is still on the shelf. The work is still ongoing. If you imagine the small dome at Tonantzintla in 1957, on the evening the plate was exposed, the dome was small and modest. The telescope inside it was a Schmidt camera with a half-meter aperture. The plate holder accepted glass plates of ordinary size. The observer logged the exposure in a notebook by hand. The notebook is preserved in the observatory archives in Puebla. The exposure lasted perhaps an hour. The plate was loaded into a wooden frame. The dome rotated. The telescope tracked. The shutter opened. The light arrived. Some of it was from nearby stars. Some of it was from the Milky Way's diffuse glow. Some of it, a particular set of photons, was from a faint blue speck 10 billion light-years away. The speck registered as a few faint silver halide grains on the emulsion. The plate was developed in the observatory's darkroom. The image was inspected. The faint blue speck was noted. The clerical hand entered it in the catalogue. The catalogue assigned it the running number, 618. That is how the work began. Nobody at Tonantzintla, on that night, knew that they had photographed the largest single black hole in the known universe. Nobody knew. The understanding came later. The work continued. The decades passed, the instruments improved. The field grew. The picture refined. And in time, by the work of many hands across many years, the speck became a quasar. The quasar became a measurement. The measurement became a number. The number became a puzzle. The puzzle became part of the active research program of modern cosmology. It all began with a plate, a small dome, a clerical entry, a clean catalogue card. That is what the work looks like. That is what it has always looked like. We do the work. We do not always know what we have done. We add to the record grows. Future generations read it. Sometimes they find things we did not know we had recorded. And sometimes, in particular cases, what we recorded turns out to be far more than we knew. TON 618 is such a case. Let me hold the broader pattern for a moment. The Tonantzintla survey was not an isolated effort. It was part of a network of similar surveys carried out across the world throughout the middle of the 20th century. Surveys at Palomar in California, surveys at Tautenberg in East Germany, surveys at Buracan in Soviet Armenia, surveys at Mount Wilson, at Lick, at La Plata, at the Cape of Good Hope. Each survey, in its own way, was contributing to a global picture of the night sky. The pictures, in their original form, were collected on glass plates, photographic emulsions exposed for hours, developed in darkrooms, examined under microscopes by patient observers. The plates were catalogued, numbered, archived. Each plate carries a small piece of the sky frozen at a particular moment, with whatever was visible at that moment recorded in chemical detail. The archives are still there, and most of the plates from the major surveys of the 20th century are preserved in observatory libraries around the world. They are no longer the primary source of new measurements. Digital detectors have replaced photographic plates for nearly all current astronomical work. But the plates persist. They are still consulted. They are still scanned, digitized, and added to modern databases. Each plate is, in some sense, a small archaeological artifact. It records what the universe looked like at the moment it was exposed. The universe has changed since. The stars on the plate are now at slightly different positions. The asteroids have moved. The variable stars have changed brightness. The galaxies on cosmological timescales have continued their journey. But the plate records the moment. And when we have reason to ask what was happening at that moment, the plate gives us the answer. TON 618, in its capacity as a plate-recorded object, has been on the plate for 67 years now. The plate has been re-examined many times. Each re-examination, with better techniques, has refined our understanding of the object. The plate itself has not changed. What has changed is what we can extract from it. This is the pattern. The data persists. The interpretation evolves. The understanding grows. Now let me bring that closer one more time, because I want to make sure we hold what this means for our place in cosmic history. We are, on Earth, in a particular position. We are in a quiet arm of an ordinary galaxy. The galaxy is one of many billions. The galaxies are spread across an observable universe that extends, in light travel terms, to 13.8 billion light-years in every direction. Within that observable volume, we have built, over the past few centuries, a network of instruments that can detect the faint flux of light arriving from the most distant objects. The flux is small. The objects are far. The instruments must be sensitive, stable, and patient. We have built them. We have pointed them at the sky. We have recorded what arrives. What arrives, in the case of TON 618, is the residual light of an event that happened 10 billion years ago in a particular small region of the universe, 10.4 billion light-years from where our telescopes sit. The light has been redshifted, dimmed, and stretched by the expansion of the universe in the interim. But it has arrived. We have caught some of it. We have measured what we caught. The measurement gives us, after all the interpretation, a mass. The mass is 66 billion solar masses. The mass implies an event horizon larger than our solar system. The mass implies a growth history that our standard cosmological model cannot easily produce in the time available. This is what we have measured. This is what we have learned. The learning is partial. The learning will continue. What sits at the end of all of this is the fact that we have done the work. We have built the instruments. We have done the spectra. We have applied the methods. We have published the papers. We have refined the estimates. We have built a record. The record is in our libraries. The record is in our databases. The record is in our memories. The record persists. Future generations of researchers, with better instruments and better theories, will read the record. They will extract more from it than we have. They will add new entries. They will refine the existing ones. They will write down what we did not yet know how to write down. This is the work. This is what it has always been. TON 618 is one small piece of the larger record. It is a particular catalogue number. It is a particular faint blue speck. It is a particular spectrum. It is a particular mass. It is the largest single black hole that has ever been catalogued by human astronomers. That fact will, almost certainly, change. The record will be displaced eventually by a more massive object that we have not yet measured. The displacement will happen. The displacement will be welcomed. It will mean that the field has continued to do its work. But for now, in the present moment, in the catalogue as we have it, TON 618 holds the title. It does so quietly. It does not advertise. It does not need our attention. It is doing what it has been doing for a very long time, and it will continue to do so for a very long time more. We are its observers. We are its measurers. We are its catalogue keepers. The work is ours. The object is the universe's. Now let us come to a quiet close. If you have come here to rest, let this carry you. The black hole does not need our attention. It does not need our concern. It is doing what it does, what it has been doing for many billions of years, and it will continue to do so for many billions more. We are only its witness. We are far away. We are safe. If you are still listening, hold this. 10.4 billion light-years from where you are sitting, there is an object so massive that its shadow alone is wider than the orbit of every planet around our sun. The object does not move. The object does not cool. The object does nothing that the cosmos does not allow. The object is older than our solar system. The object is larger than any single thing our cosmological models can easily produce in the time available. The object sits in a corner of the constellation of the hunting dogs, a point of light, faint, blue-white, no larger to our telescopes than the head of a pin held at arm's length. The catalogue number is 618. The community calls it, with the brevity that astronomers prefer, TON 618. That faint point of light is the visible record of the largest single black hole that human beings have ever measured. It breaks the universe in the sense that it sits beyond what our standard models comfortably allow. It does not break the universe in any literal sense. The universe is intact. The universe contains it. The universe has always contained it, for as long as it has been there. What it breaks is our description. Our description is incomplete. Our description will, with time and more work, become more complete. That is what we have walked through tonight. The object is at 10.4 billion light-years. Its light arrives at our telescopes now. It has been arriving for nearly 7 decades, since the plate at Tonantzintla first captured a few of its photons. It will continue arriving for as long as we point telescopes in that direction. It is, by every meaningful measure, the largest single black hole that has ever been catalogued by human astronomers. Tonight, we have walked through what that means. Thank you for staying with me through this story. Ameh.